So this video is gonna take us through the basics of titration, no pun intended. What you are learning in this video is crucial to helping you do titration calculations for titration curves, as well as buffer calculations for buffer solutions. So you got to get this part down to have the rest of it make sense. So basically, titrations are a neutralization reaction as far as acids and bases go. There are other types of titrations, but for acids and bases, you're really doing a neutralization reaction. Acids neutralize bases. So the big idea behind an acid-base titration or an acid-base neutralization is that you're taking the H plus and the OH minus and neutralizing them with each other to create water. So this is the underlying reaction that happens when you do an acid-base neutralization. So since we have to react all of the H plus and all of the OH minus, at the equivalence point, at the end point, when the titration is finished, the moles of H plus should equal the moles of OH minus so that there's no extra of each, and you have a neutral solution. All right, so moving on to more math, we're developing an equation here. We know that the moles of H plus out of any acid is going to be the molarity of the acid times the volume of the acid, right? Molarity times liters equals moles. But since we want the moles of just H plus and not the moles of acid, we also need a mole ratio, the moles of H plus per an acid. So if you have hydrochloric acid, it's a 1-to-1 ratio. But if you have phosphoric acid, it's a 3-to-1 ratio. So you get 3 moles of H plus for every mole of acid. Same is going to hold true for bases. The moles of OH minus is going to be equal to the molarity of the base times the volume of the base times the mole ratio. So calcium hydroxide will have 2 OH minuses for every 1 calcium hydroxide molecule. So we know this is true, we know this is true, we also know this is true. So that lets us develop what is referred to as the titration equation. So you set these two equations equal to each other, and you get the molarity of the acid times the volume of the acid times the mole ratio, gives me moles of H plus equals moles of OH minus. So this is the idea to what happens when you titrate. This is mathematically what has to be true. So oftentimes when you do a titration, you're trying to figure out what is the molarity of the base, or what is the molarity of the acid, or volume for that matter. Okay, so you need to use the mole ratio because there's chances that you could have more than one hydrogen, like sulfuric acid, or you could have more than one hydroxide, like magnesium hydroxide. So you've got to be aware of what the mole ratio is, in addition to just molarity times volume, so that you make sure you are actually neutralizing all the moles of H plus with an equal number of moles of OH minus. So that's the basics. What we're going to do now is work our way through 3 different kinds of titrations. The first one is going to be very simple, because the first one is a titration between strong acids and strong bases. So if you remember, a strong acid and a strong base dissociate or ionize 100%. So everything breaks up into H pluses and the anion, everything breaks up into the cation and OH minuses. So therefore, you have all of the H pluses available, all of the OH minuses available, you're done. The pH is 7 when you have a strong acid and a strong base. You are going to see that that's not actually true if we're using something that is weak. So really, if you have a strong acid and a strong base, all you have to do is solve the titration equation to figure out what the pH is going to be. Actually, technically, you don't even have to do that because you know the pH is going to be 7. All right, so let's just do a couple of examples using that titration equation so that it refreshes your memory, you're comfortable with it. So first example, how much of a 1.125 molar HCl solution is needed to neutralize 75 mils of a 0.1 molar? So here we're looking for a volume. With this titration equation, you can technically leave the volume in milliliters when you are only doing titration. If you're doing anything other than titration, you can't, and you'll see that as we move forward. So here's my neutralization reaction. It's always good to write that down. So HCl plus sodium hydroxide is going to give me water and sodium chloride. Everything's 1-to-1 in this case. So all I have to do is use this equation. These kind of fall out because it's a 1-to-1 ratio, but I've included it anyway. So if I rearrange the equation to get the volume of the HCl, molarity times volume times mole ratio of base, divided by molarity and mole ratio of acid, plug in my numbers, I get 60 milliliters. Okay, so a 1-to-1 ratio H plus to OH minus gives me 60 mils of HCl needed based upon what I have. But what if I don't have HCl and sodium hydroxide? What if I have things that have more than one H plus or more than one OH minus, or both in this case? Okay, so here I have sulfuric acid, H2SO4, and aluminum hydroxide, AlOH3. So same concentrations, notice the acid is still 1.125. I'm still using 75 milliliters of the 0.1 molar base, but because I have H pluses and OH minuses that are different, the volume of the acid that I need is not going to be 60 mils. So again, if I write my balanced equation, I see that it's going to take 3 moles of sulfuric acid to balance out 2 moles of aluminum hydroxide, and so forth. That really doesn't change what I'm doing to the equation, however. Remember that it's not the coefficient out here that matters, it's how many OH minuses are in the aluminum hydroxide. So for every 3 moles of aluminum, or for every 1 mole of aluminum hydroxide, I have 3 moles of OH. For every 1 mole of sulfuric, I have 2 moles of H+. So this mole ratio area becomes much more complicated, obviously, because you have more than one H+ and OH-. But the setup is still the same. Mathematically, however, notice that I get 90 milliliters instead of 60 milliliters because of the variation in the mole ratio. Okay, now this equation is complicated enough that you could also solve it doing typical dimensional analysis. Take this, multiply these two together, you're going to get moles of OH, or moles of aluminum hydroxide. You can use the mole ratio, 3 moles of sulfuric on top to 2 moles, because that's essentially what we have, right? 3 moles of sulfuric acid on top, 2 moles of OH- on bottom, to get into moles of H2SO4, and then divide that whole thing by the 0.125 molar in order to get your liters. So you could use dimensional analysis to solve this. You wouldn't have to use the titration equation. It's kind of 6 of one, half a dozen of the other. All right, so there is a titration with strong acids and bases. It's going to be a little bit different when we go to weak acids or weak bases. We're only going to do one or the other. If we do both, that gets really crazy, so we're not going to bother doing both. I've never seen AP ask you for that anyway. But I think I'm going to stop the video here, and we'll just start a new one up in order to do the weak titrations.